Uh, yeah, Good morning, everyone, and thank you, IEEE for this invitation for the talk. So I'm Christo Thomas, and I'm here to talk about next generation A for next generation wireless networks. So the talk will be mostly about the current limitations of AI native wireless networks, and how we should actually design the next generation AI solutions for wireless system if we are to meet the stringent requirements of next generation applications. Uh, yeah, so so this is just a brief bio about myself. I'm currently postdoctoral associate at Virginia Tech with Professor Walid Saab, and I am an aspiring faculty candidate also. And I did my PhD in Eurocom from France, and I have some few years of industrial experience with wireless semiconductor industries, specifically working on 5G or 4G modem devices. So before going into the details of my talk, let me try to give some introduction to the topic. So as we all know, wireless systems or wireless technologies have evolved from first generation to the fifth generation. So along these transitions, the data rates have skyrocketed from mere kbps levels to almost Gbps levels of um, Gbps levels of data rates, and also the underlying communication technologies have changed from packet switch data transmission to CDMA, OFDMA, and to massive MIMO OFDM system, along with the introduction of AI into wireless systems. So, and the fifth generation of wireless systems actually, actually supports exciting set of applications, not just enhanced mobile broadband. So that includes massive machine type of communications or ultra reliable low latency communications and so on. So now here our question is like, now, so where do we see ourselves after 5G? And the answer is obviously sixth generation of technologies. So while we transition to 6G, so we expect that a lot of exciting set of applications awaits us, like brain level metaverse experiences where a human XR user can actually be teleported to a virtual world with its own cognitive avatars, and next generation AI augmented digital twin applications. Uh, Next generation AI augmented digital twin application or autonomous networks where network itself can actually perform self-healing or self-optimization. So traditionally, the approach to transitioning from one G to another G is through evolution in wireless technologies, like we transition from single antenna to multiple antenna technologies. Then we move to terahertz, or right now we are at millimeter wave band of communication. In future, we expect that we move to terahertz bands and reconfigurable intelligent surfaces where we can actually manipulate the wireless environment itself, and then advanced multiplexing schemes and so on. However, given these wireless physical resources are limited, okay, if we are to support the future wireless system requirement, we need to make the communication more efficient as possible. So the usage of communication and computing resources should be much more efficient. So here we expect that introduction of AI into different layers of communication networks can actually help with using the resources in a much more efficient fashion as possible. So that's the concept of AI native networks, where we can see the introduction of AI into different functions, be it design of physical layer functions, or control, resource allocation, or management of wireless networks. We can see the introduction of AI. So that's the concept of AI native wireless networks. Yeah. So now, So let's now look at the uh, future wireless networking challenges that this new set of applications bring towards us. So first one is the intent management, which actually means that, okay, network should be able to autonomously translate any high-level business into low-level network configurations. For example, okay, the network operator wants to minimize the energy consumption to around, let's say, 80% from current usage. So then, okay, the network should be able to translate that requirement into low-level network configuration in terms of how it performs resource allocation or beamforming and so on. Second is the resilience aspect. So recently there has been network outages throughout the nation where that actually resulted in billion-dollar loss to the economy. So resilience is the aspect of how we can actually withstand, how the network can withstand any network disruptions. Third is the cognitive networks aspect, which means network should have human intelligence capabilities. So it should be able to perform self-optimization, self-configuration, and so on. Fourth is the ability to handle nonlinear signal dynamics, be it the nonlinear nature of underlying wireless channel models or even the multi-modal data also. So fifth is the situational awareness to wireless environments and dynamic adaptability to changing wireless tasks and wireless environments. Finally, there is also the ultra synchronization and time criticality, which is actually very critical for digital twin based applications where there should be high synchronization between physical and digital worlds. So that's where the ultra synchronization challenge comes in. So now, given these future wireless networking challenges, how can we leap into a new G of wireless technology? So that's the question we ask here. And for that, as I mentioned, the usage of AI is going to be very critical. But let's look at the current state of the art of AI native wireless networks. So currently, we predominantly use data-driven AI methods like convolutional neuro CNNs or RNNs, autoencoders, and so on. However, they are limited by the following aspects. So their performance rely on large volumes of data. However, in wireless system, data need not be abundant always. Second is they are black box model and they cannot explain the decisions they make. So most of these AI models also rely on a centralized server to perform training, which actually results in a lot of communication overhead between the edge devices and the server. And fourth is their lack of performance guarantees, unlike in model-based signal processing algorithms, where their performance can be accurately characterized in terms of system parameters. Fifth is the limited adaptability to unseen and new environments, plus catastrophic forgetting. And finally, these AI models lack autonomous nature, which is very critical for future wireless applications, as I mentioned before. So here, so given these limitations of the state of the art, so we have identified certain key qualities next generation AI should have if they are to be deployed for next generation wireless networks. So first one is the explainability aspect. So explainability means, which actually means that these AI models should be able to explain the decision or able to find the root causes if there are any performance deviations and so on. Second is the reasoning and generalization to out of domain or out of data distributions. Third is they should support green and sustainable computing if we are to meet the sustainability goals of future wireless networks. Fourth is they should be able to perform long-term planning, which means that if there are any network disruption, they should be able to plan the network actions like resource allocation or physical layer functionalities and so on. And they should also support distributed computing or distributed reasoning, thereby enabling collective intelligence among multiple edge devices. Finally, they should also have common sense behavior. So common sense is something which allows humans to get out of any unforeseen scenarios. So we think that the wireless networks also should have this common sense behavior if they are to get out of any unforeseen cybersecurity issues or disruptions in the network. Yeah, so given these, so now that we actually have identified these key qualities, in fact, in the AI literature itself, some of these qualities I mentioned, these are like holy grail of AI research itself. So here we think that the development of next generation AI should go in tandem with the next generation wireless networks if you have to be able to meet all these future networking goals. So that's the message I want to convey here. Yeah, so now before going into the details of the technical details further, I just want to summarize the research contributions I have done along, which goes in tandem with the vision I have mentioned before. So during my PhD, I actually worked on massive MIMO systems, beamforming, and other related signal processing algorithms. And now, during the last 2 years of my research as a postdoc, I'm actually working on reasoning-driven semantic communication, which is expected to be a front runner of 6G or beyond technologies. And during this time, we have also developed a rigorous vision for next generation technologies using artificial general intelligence-based AI models. So what we actually have found is that, future wireless networking research should be a multidisciplinary collaborative effort between wireless, next generation AI, signal processing, and control communities. Yeah, so that's the message I want to convey. So further, I will go into the details of semantic communication, which is the topic I've been working over the last 2 years and is going to be the front runner for 6G and wireless and beyond wireless system. And we are also editing a book on semantic communications, which is the first of its kind in the literature. Yeah, so before going into the details of semantic communications, I would like to give some motivation. So let's look at the classical communication system. So in classical communication system, the objective has been that the transmitter communicates these messages in such a way that receiver is able to recover them with arbitrary, low probability of error as possible. So that is the technical aspect of communication, as is pointed out by Warren Weaver in his seminal contribution. But there are two other levels of communication which has been ignored so far in the literature. So second, the level B is the semantic problem, which means how precisely do these transmitted messages convey meaning? And third, level C is how effectively does the received meaning affect the conduct at the receiver side in the desired way? So that's the effectiveness problem. So yeah, so as Shannon has pointed out in his seminal work, so frequently these messages have meaning, but the semantic aspects of communication are irrelevant to the engineering problem we deal with. So far, until the 5G, this approach to technical problem has worked very well in that we are able to reach close to Shannon's information capacity levels. But when we go to future wireless systems, we have more stringent requirements in terms of the quality of service. At the same time, so we are supposed to connect billions of devices, while supporting metaverse or digital twin-based smart environments and so on. So now we need to make the communication more efficient as possible. So here, one promising approach is the concept of semantic communication, which actually means that convey the meaning behind the messages in such a way that receiver is able to regenerate those meaning behind the data with arbitrarily high probability of a high fidelity as possible. So that's the definition of semantic communication. So now here the question is, what is the semantic behind the semantic communication, or what is the meaning of messages? So for that, let's look at the state of the art on semantic communication. So in one prominent approach in semantic communications is the deep joint source channel coding approach. So where, so traditionally, we used to separate the source encoding and the channel encoding part. And as per Shannon, there is no loss of optimality in the infinite block length regime when we do this source and channel coding separately. But if we perform jointly source and channel coding, we can actually lower distortion for a given finite block length than performing separate source and channel coding. So in deep JSCC, the approach is that, so we replace this JSCC encoder and decoder with a AA module, and we perform end-to-end training in such a way that, some semantic loss is minimized. So that's the goal of deep JSCC approach. So while performing this deep JSCC, we are able to get high compression. So we end up transmitting only the relevant content behind the messages. So that's the state-of-the-art approach to semantic communication. But our vision on semantic communication is slightly different. So we think that if we can instill reasoning behaviors at the transmitter and receiver side, for example, if let's say a receiver has some good generative AI capabilities where receiver is able to reconstruct or predict future data with very less amount of information communicated. So then we can the transmitter can afford to send very less information as possible. So we can rely less on the channel, but more on the computing capabilities at the receiver side. So that's the vision we propose towards semantic communications. And so basically we propose that we should transition from data-driven approach where we used to look at discrete elements like channel values or quality of service values to actually reasoning-driven networks where we can where we not only use generalizable or explainable machine learning algorithms, but the network is able to perform deductions or logical reasoning from the very less amount of information communicated. So that's the reasoning-driven wireless network concept we are proposing here. So specifically in semantic communication, we look at some few challenges. So so my further talk will be based on a paper which got published in IEEE Transactions on Wireless Communication. And for this paper, we actually looked at 3 distinct challenges. So first one is the minimalism in communication. Second is the generalizability to out-of-domain or out-of-data distributions. And third is the high fidelity aspect. So apart from these 3 challenges, so there are other open challenges like interoperability. So if you have multiple semantic communication users that speak, let's say, distinct languages, how we can build an interoperable SC system. Then there is the resilience aspect, resilience to various network disruptions. And finally, how we can actually integrate these SC principles into the existing OSI or ORAN architecture without introducing significant interoperability or standardization challenges. So that's the final challenge. So I envision that I envision to look at these remaining challenges in my future research. And so that's the let's now go into the details of the paper. The paper which got published in Transactions on Wireless Communications. So here we look at a point-to-point semantic communication system, where the transmitter is called a teacher and receiver is called an apprentice. So the meaning why we call the transmitter and receiver so hopefully become clear as the time progresses here. So the transmitter or the teacher observes the world environment state and extracts the entities from the world state. And there is a semantic state descriptor module, which actually, semantic state descriptor extract the semantics present in the data, which actually belongs to W, which is the syntactic space. And then there is an encoder, which actually encodes this semantic states. And this encoded output belongs to the representation space U. And it gets communicated. And at the receiver extract the semantic state from the data received, and the apprentice performs certain semantic reasoning. With these reasoned outputs are being used to perform certain actions on the world state. So that's the concept here. So here we look at two distinct problems. So one is the reasoning problem, so which can be, okay, so basically we ask two different questions: how to rigorously define and learn the semantics present in the source data, and at the same time, how to perform deductive reasoning by evaluating the logical formulas at the receiver side. So that's two different problems we consider here. And there is also the emergent language problem. So which is basically at the start of communication, teacher is not aware of the semantics receiver is interested in, and receiver is not aware of how the teacher is going to perform encoding at its end. So in order to learn this encoder and decoder, which are mapped as probabilistic distributions, we use this emergent language problem concept. So emergent, we call this emergent because at the start of communication, both doesn't have any idea about intentions of the transmitter or the receiver. So that's why we call this emergent language. So before moving into the reasoning problem details, I would like to introduce two different reasoning methodologies in AI community. So first one is the causal reasoning. So causal reasoning is founded on the principles of three different components. So first one is the causal discovery. So causal discovery means learn the causal structure within the wireless data as a directed acyclic graph. So this directed acyclic graph involves the cause and effect relations between different variables present in the data. And second is the causal representation learning, which means that mapping the large dimensional input observations to lower dimensional representations involving just the causal variables. For example, if you have a large dimensional antenna measurements, we need to first convert it to a lower dimensional representation, which involves just the causal variables. So these causal variables here could be the cause and effect relations between different scattering components present in the environment, and how they actually lead to a particular channel component, for example. And finally, there is the causal inference. So given this causal graph, causal inference, we can perform interventions, which actually means that we can actually replace certain variables, values of certain variables in this causal graph, and see what are the effects those variables make on the effect variables. Then there is also the concept of counterfactuals, which actually means that we can imagine completely different worlds. So that actually means that we can actually change the random process that actually generates some of these endogenous variables in this graph. So that's the concept of counterfactual. So interventions and counterfactuals can actually lead to out of data distribution generalization. So that's the advantage of using causal reasoning. And second reasoning methodology is called neuro-symbolic AI, which is basically a combination of symbolic AI. Symbolic AI is basically composed of symbols and logic, or the relations between the symbols. For example, knowledge graph is one symbolic AI method where we can represent the relations between different symbols as a graph, and these graphs are explainable. And the second methodology is the neuronal AI, which is actually composed of neural networks, which has very good statistical prediction property. They can handle uncertainty well. Some examples, but there are disadvantages, like they cannot generalize beyond the training distribution, or they are black box models. So if we combine the advantages of neuronal and symbolic AI, we get neuro-symbolic AI, which has the advantages of explainability, generalizability, and they can perform hierarchical abstraction also. So given this reasoning methodology, at the transmitter side, so how we actually tackle the transmitter reasoning problem is, So given the entities extracted from the data, okay, so we identify those entities which are actually relevant to the receiver. So those entities are called semantic content elements. Okay, given these semantic content elements, we form a directed acyclic graph that involves the cause and effect relations between different variables. And we learned this directed acyclic graph using a recently popular AI method called generative flow networks, where we can actually iteratively learn each causal edge starting from an unconnected set of entities. So then we encode this DAG, communicate it, and at the receiver performs certain logical reasoning. So after receiving these causal states, it actually combines them through these certain logical connectives, logical or and connectives. So that is the logical formula receiver evaluates. And okay, for that we use a neuro-symbolic AI methodology called logical neural networks. So okay, the results of this logical reasoning problem is used to, results are used to perform certain actions on the receiver's wireless environment. So that's the reasoning problem which we consider here. And yeah, so next I will talk about the emergent language problem which I was mentioning. So here the teacher is okay. Teacher doesn't want to communicate much. I mean, teacher intends to communicate very less amount of semantic information because that's the goal of semantic communication. And okay, at the same time, receiver's intent is to regenerate maximum semantic information as possible if it has to perform certain, if it has to perform its task very effectively. So given these two contrasting goals of teacher and apprentice, okay, a natural solution is to consider a game, consider this as a game. So specifically, this is a signaling game because of the communication involved between teacher and apprentice. And okay, we can learn this teacher encoder and apprentice decoder as Nash equilibrium solutions of this signaling game. So that's the idea we propose here. And as is shown here, okay, transmitter objective is to maximize the negative of average semantic information communicated from its end. For that, okay, we need to formulate novel semantic information measure. So here how we actually formulate semantic information is using the concepts from category theory. So basically, category theory allows us to group objects having some similar properties or relations between each other. So basically, a category consists of different objects, and there are morphisms between these objects, which actually basically are which can be seen as the causal relations between different objects present in the category. So let's say we have a category of causal state descriptions, and let's say, for example, we have a word red. Okay, there are several possibilities that can follow from red, like it could be red car, or it could be red meat, or red blooded, and so on. So all these logical conclusions that can follow from this particular word red, okay, that actually can be seen as capricious from category theory perspective. So the information contained in this logical entailments, that is the semantic information transmitter extracted from the data. So that's the concept we use here. So similar to the transmit semantic information, we also formulate the received semantic information, which will be a fraction of the transmitted semantic information. And this fraction is equal to the semantic similarity. Semantic similarity between the actual causal state communicated as well as the reconstructed causal state. So let's now so we also, apart from this signaling game, as I mentioned here, we also looked at the Nash equilibrium analysis for our game, and we looked at some trivial cases where we don't achieve an optimal solution, like pooling equilibrium, where the cardinality of U is 1. So that means you communicate just one symbol regardless of the causal state. This is minimalistic, but that does not lead to high fidelity at the receiver side. And there is separating equilibrium where the cardinality of U and W is same. And what is more interesting is the partial pooling case where the cardinality of U is less than that of W, which means that, okay, we intend to communicate at a lower representational space, lower dimensional representational space, but that should also ensure high fidelity at the receiver side. So our analysis actually shows that, okay, an optimal transmit signal partition is a Voronoi tessellation of the syntactic space such that, okay, if you consider, okay, this to be the set of all causal state, we partition in such a way that, okay, we transmit UK for all the causal state that leads to same semantics at the receiver side. So that's the Voronoi tessellation we ended up with. So compared to classical system, so this partitioning is actually in the semantic space and not in the Euclidean space. So that's the message I want to convey through this analysis. Yeah, so I would also like to, pinpoint certain key analytical results we had. So first one is the semantic information, as I mentioned. So basically, we created two categories. So one is the syntax category, which is the category of all the causal state. And there is a semantic category, which is basically involving all the logical conclusions that follow from any causal state. So the mapping between the syntax to the semantic category, so that actually defines the semantic information conveyed by the transmitter. And we also looked at the minimalism aspect, where we actually derived the average amount of bits communicated. So we saw that the lower and upper bounds of this average amount of bits communicated are much lesser than that of the classical system. So that actually proves the minimalism aspect. And we also looked at semantic error probability measure. Okay, we derived a lower bound of this semantic error probability, and we showed that this lower bound is less than or equal to the lower bound on the probability of bit error for a classical communication system. So what this tells us is that, okay, even if the probability of bit error is less, it is possible that a receiver is able to reconstruct the semantics properly. So as long as semantics is recovered properly, yeah, so that is good enough for receiver to execute its task. So we must transition from, okay, this probability of bit error measures to semantic error probability measures for the future wireless systems. So that's the message these results tell us. So finally, I would also like to show certain simulation results which we had. So we specifically used a image data set where, okay, basically a visual question and answering based image data set, where the receiver's aim is that, okay, after receiving the images, receiver aims to answer certain questions based on this image. So that is the logical conclusion from the receiver point of view. So, and we simulated these data sets, these goals for different tasks, where, okay, each task has overlap in terms of the syntactic space, but as task number increases from task 1 to task 4, we actually we increase the size of this syntactic space. And what we saw is that as time progresses, the amount of time required for the emergent language phase reduces to 0. So this shows that as time progresses, the system is able to, the receiver or transmitter is able to gain more knowledge. So that actually shows the generalizability aspect. And we also showed the minimalism aspect, okay, where we actually, okay, simulated the average amount of bits communicated for the semantic system. And we actually see that, okay, we need lower number of bits to communicate compared to classical system or even state-of-the-art JSCC semantic communication systems. Yeah, so that's the two messages I want to convey from the simulation results point of view. Yeah. So now, okay. So now, one question which we actually, we consistently get is that what are the applications of these semantic communication systems? We don't think that, in the near future, semantic communications, given the large amount of computations involved, if you have to deploy these next generation AI methodologies. So cellular, or mobile broadband need not be the best applications for semantic communication. But there are other applications like digital twin based smart factories or smart cities. So there actually, semantic communication could be a very useful approach, given that this involves a lot of sensing measurements being communicated from the different devices, and then base stations or the edge servers forming a digital twin of the wireless environment and so on. Here, the semantic communication can actually be a promising approach. So here, in our next work, which got accepted in IEEE journal on selected areas in information theory, so we looked at causal semantic communications for digital twins, where we specifically looked at applications like, let's say there is a base station with the digital twin at its end, which actually controls different autonomous robots in a smart factory, for example. And this base station has access to a lot of sensor measurements. So we call this base station the expert agent. And receiver, for example, this could be autonomous robots. They may not have very high computing capabilities. So we call them imitator agent. So the expert agent's goal is to, using these sensor measurements, expert agent forms a world model about the environment, for example, this factory environment. And using this world model, it actually computes an optimal policy these actuators of these autonomous robots should perform, and then communicate a concise representation or causal representation of the world state to the imitator agent. And imitator agent, using the reduced or the abstract information it receives, it also forms a world model, but it need not be as accurate as the world model developed at the expert agent side. And the goal is here for the imitator to actually generate an imitator policy that is quite close to the expert agent policy. So we use the concept of causal imitation learning to actually learn the imitator or the expert agent policies here. And so this system model which we consider, we think that this can actually be useful for digital twin enabled 6G ORAN systems also, where in ORAN architecture we have a 5G or a 6G core which has large amount of computing capabilities. This 6G core or the cloud servers can actually build a digital twin of the wireless environment of the network or the network architecture itself. And there are lower layer components like control unit or radio unit and near-time radio intelligent controller and so on. So they also need to perform real-time network operations like real-time beamforming or real-time channel estimation and so on. So this digital twin-based 5G or 6G core can actually communicate or concise representation of the world state. And this information can be used by the lower layers to perform real-time network operations. So that's the application to which this particular system model can be applied. And so I will not go into the details of the mathematical formulations here. So here, compared to our previous work, we actually distinguished causal information from mutual information. So in mutual information, which is the traditional information measure, does not distinguish the directive nature of information or does not take into account the cause and effect nature of relation between different variables. So here we use the concept of integrated information theory from neuroscience to actually define the causal information. We use the concept of integrated information to actually define the information conveyed by a network state, which is actually composed of certain constituent states also. And this integrated information theory's advantage is that, okay, integrated information actually tells us that information conveyed by this network state is beyond that is conveyed by the information from the constituent states. So this actually means that integrated information can actually that can actually quantify the causal relations between different constituent states in the network. So that's the concept we actually use for information. And for designing the world models at the transmitter and receiver, we use the concept of world models in AI literature. So where, okay, world models in AI literature is a cognitive architecture, which is composed of several modules like sensing. Then there is a perception or world and perception and a world model, plus a actuator which actually performs action or planning. So that's the, so we followed similar architecture. So where we have a lot of sensing information, then we use a graph neural network to actually learn a causal graph from the entities, and then and a variation encoder, variation autoencoder that actually can actually represent that can give us a latent representation of this network state. And there is an RNN which can actually perform prediction of the future states. And this prediction of future states can actually be used to perform certain planning, like, what are the future network actions the transmitter or receiver should take. So that's the cognitive architecture of world models which we use in this particular work. And so we also have some key analytical results that followed from this work. So specifically, okay, the results 1 and 4 here. So which this shows, the results 1 and 4 here shows that, okay, if we can get a accurate physical environment modeling, okay, we can, the network can actually perform better prediction of the future states. And specifically, if we use generative AI capabilities, we can actually close the gap, close the gap in terms of the prediction capabilities at the receiver side and at the transmitter side. So basically, we actually have shown through simulations that as communication progresses, receiver gains more knowledge about the world environment. And then, okay, using this generative AI capabilities, it can actually come very close to the transmitter world models. So that's the message I wanted to convey. And for these causal relations, as I mentioned, we use certain concepts from algebraic topology, specifically the concept of simplicial complex, to actually model the cause and effect relations. So simplicial complex consists of different simplices, whereas simplice is actually a convex combination of several data points. So here, okay, we actually specifically consider first order. A causal graph can actually be viewed as a first order simplex, where in first order simplex we have two different points, which is forming a simplex. So here, if we consider causal edge between two different variables, that actually forms a first order simplex from algebraic topology perspective. And using this algebraic topology results, we use them to actually formulate novel semantic information or semantic reliability and similarity matrices. So that actually concludes my previous 2 years of research. I would also like to pinpoint the future directions in which I would like to work on. As I mentioned in my previous slide, in semantic communication, one of the challenges which is remaining is how can we integrate these SC principles into the Open RAN or OSI architecture? So here, how I envision it to happen is that, okay, so we need to have an external module from all this communication layer, which is called a semantic brain, that actually can actually extract the semantics present in the data. And using the information, semantic information extracted, it can be used to control different layers. Like, the semantic information can be used to assist reasoning-based physical layer functionalities like channel estimation or beamforming. And in layer 2, we can actually use this semantic information to design causality-aware scheduling algorithms. And no, if you have, okay, in future wireless system, we will move from quality of service to quality of personalized experience as the metric. So we can, okay, using the feedback from the receiver and the semantic information extracted, we can actually model QoP handling modules at layer 3. And we can also have a knowledge base at the 6G core, where this knowledge base can actually store the history of semantic information. And this history of semantic information is essentially the transmitter has to perform prediction of the future events in the wireless environment. So as I see here, okay, this step-by-step introduction of semantic principles into different OSI layers can actually, okay, that can make this smooth introduction of SC principles into the ORAN architecture without posing a lot of interoperability or standardization challenges. And apart from this, I also have a bigger vision where, okay, so this is based on our previous work where we actually developed a rigorous vision of future wireless systems that are based on artificial general intelligence based algorithms. So we actually proposed a cognitive architecture for the network. We call it telecom brain, where we actually think that, okay, in AI literature, okay, most of the cognitive architecture are based on instilling the autonomous capabilities or the cognitive aspect to the different autonomous agents. But we think that, okay, when it comes to wireless network, okay, network should have network should also have a world model at its end, where it can actually understand how this different objects in the world works. For example, if we are if you're building a smart transportation system, okay, so the network should know, okay, how different objects like different vehicles, or like if there are humans in the road, how they will actually behave. If a digital twin-based base station is to control these different autonomous agents, it should know the behavior of, it should know how these different objects actually behave. So it is essential that network should have this brain architecture instead of just instilling it in different autonomous agents. So that's the concept we actually propose in this research vision. And this opens up a lot of problems in terms of sensing, perception, how the network can actually form abstract representation about different entities present in the wireless environment, and how to construct a world model, and how to perform action planning at the network side. So I envision to work on these exciting challenges ahead of us. And another thing is, I want to just point out is that, okay, while we develop these next generation AI solutions specifically for wireless system, okay, we should also be able to let me just start by saying that, okay, currently in AI literature, there is a lack of mathematical frameworks that can actually specify these AI models. And recently, there has been advances in using category theory for modeling geometric deep learning-based algorithms. So motivated from these principles, I envision that we should be able to use these frameworks from category theory or algebraic topology to actually specify the fundamental building blocks of, say, neuro-symbolic AI or causal reasoning-based algorithms that are expected to be the front runners for next generation wireless solutions. So that's also a quite important task which you should focus on. So that ends my talk, and I'm happy to take any questions if you have.